Good morning. My name is Sudhakar. I am going to teaching about the basic manufacturing technology. In that, we are learning about the lathe machine and lathe machine operations. Right. In a previous class, we have discussed about the methods of taper turning. What are those methods? Can we recall it? One is form tool method, and the second one is swivel compound rest method, and the third one taper attachment method. Right? Before going to discussing about the today's class, can we recall this class, yesterday's class? In farm tool method, right? In this method, the tool is having similar shape, which is produced on the workpiece. That is, we want in taper turning means we have to produce some inclination, right? The diameter is gradually decreasing or increasing. That means it is in inclination position. That inclination also should so that inclination is produced by our farm tool. That farm tool is in the form of our workpiece which we are going to produce on the workpiece. The farm tool is having the shape which is we are going to produce on the workpiece, right? That so this method is called form tool method. In this we need angle alpha. That angle alpha is calculated by some formulas. So by that we can do this operation, right? And the next method is compound rest method. In compound rest method, we are having decrease on the compound rest. On this decrease, the compound rest is swiveled with our required angle. With that angle, we are doing the taper turning operation, right? So we are having one formula here, that is tan alpha equal to T minus D by 2L. Capital D means large diameter, small d means smaller diameter, and length L is the length of the workpiece, right? So in these two methods, here the length is the problem. Why? Because the form tool method, the tool is having some width. With that width only, we are producing the taper shape on the workpiece, right? So here the length is the limit problem. To overcome this problem, we are using compound rest method. Here also length is some limit, right? Why? Because the compound rest is moving to some distance only on cross slide. So for that reason, here also length is limited. But compared to farm tool method, here the length of the workpieces are more, right? So we are producing taper shapes more here in compound rest method compared to farm tool method, right? Now the last method in this yesterday's class is taper attachment method. In this taper attachment method, we need a special arrangement, that is a bar stock, and in that we are a bar, right? So that bar is having graduated angles, graduated degrees. So on that bar stock, this bar is swiveled with the required angle. Where this bar is attached, it is attached to the cross slide on the opposite direction to the cross slide. To do this operation, the cross slide is not connected with cross slide mechanism. It is attached to the taper attachment. So for that, if the cross slide is so for this, we are moving our cutting tool is parallel, but we are getting the taper shape. Why? Because the cross slide is attached to the taper attachment. In the taper attachment, we are provide the bar stuck in some degrees. So inclination is getting there. So with that inclination, the cutting tool is moving. With that inclination, we are getting the taper shape on the workpiece, right? So in this, the length of the workpiece is more, right? So here the length of the workpiece is less. That means taper shape is less. Here also taper shape is mediator, and in this the taper shape is more. right? Now the last method is taper turning by tailstock set over method. Okay, so that method is used for small tapers on long jobs. So we are producing the small tapers on long jobs. We are using this procedure, that is taper turning by set over method. The tailstock center is moved to an offset. The tailstock center is moved to an offset. We will observe in this figure. Amount of offset depends upon length of work and taper dimensions. Tool is fed parallel to the lathe axis, right? So again, we can learn this. This tailstock set over method is used for small tapers on long jobs. The tailstock center is moved to an offset, right? Amount of offset depends upon length of work and taper dimensions, and the tool is fed parallel to the lathe axis. Now observe this. So this is our workpiece. Here it is having this taper shape. So this is the large diameter capital D, and this is one is the small diameter small diameter D, small d. So this is the total length of the taper shape. This is the overall length of the workpiece. OL means overall length of the workpiece. TLL means taper length of the workpiece. Now we are observing this tailstock set over method. Already we have seen in yesterday's class for this procedure by some video. After this method, we are again observing some animations on these taper methods. After this method, right? We can observe here. This is our chuck, right? This is our chuck, and here the tail stalk. Actually, the tail stalk is on the similar axis to this spindle axis. So this is the spindle axis. So this tail stalk axis also actual here it is coincide with this spindle axis. But in this tailstock sector method, we are moving this tailstock with some distance, some inclination to this spindle axis. Observe here, this is the spindle axis, right? But here tailstock axis is here. This is the tailstock part, and its axis is here. So we are having some distance between the spindle axis and the tailstock. So this movement is called tailstock set over method, set over, or it can be called it as offset. So this distance is called tailstock offset or set over, right? So by providing this, after providing this, we are moving our cutting tool in parallel to this spindle axis only. We are not providing any angle onto this cutting tool. We are not providing, we are not swiveling our cutting tool. Okay. So this is the diagram showing the tail structure for method. Here, this is the check, and the tail stop. Right. In between, we are fixing our workpiece here. Okay. This is our cutting tool. So the distance between the axis of the spindle to the distance of the center of the tailstock axis. The distance between the spindle axis to the tailstock axis is called S, that is called set over, right? So this is the length of the taper and this is the total length of the workpiece. Okay, the workpiece is rotating in this direction and we are giving our feed. We are giving feed in parallel to the workpiece axis. Understood? We are giving feed to the cutting tool parallel to the workpiece axis only. We are not giving any inclination angle. We are not providing any angle on this to this cutting tool. We are not providing any angle to this cutting tool. Just we are offsetting this tailstock. That value, this S value is important. This method, right? That can be calculated by doing this. So these are the two centers. This is tailstock end, and this is the headstock. So this is our workpiece axis, and this is the headstock spindle axis, right? This is the workpiece axis, and this is the spindle axis. So the distance between the tailstock axis and the spindle axis is called S, that is set over, and this is the total length of the workpiece, capital L, and this is the length of the taper, okay, and this is the inclination angle alpha, okay. Now in triangle ABC, sin alpha is equal to BC by AB, right? BC by AB. For small angles, tan alpha is equal to sin alpha. Sin alpha is equal to tan alpha for small angles. Small angles. So now, what is BC? Is the amount of set over, and AB overall length of the workpiece. Now, S is equal to, from this figure, S is equal to BC, S is equal to BC, and BC is equal to AB, sin alpha is equal to tan alpha, that means AB tan alpha, S is equal to BC, that is equal to AB tan alpha. Now, AB means capital L, so that's why S is equal to L into tan alpha. If the angle alpha is very small, alpha tan alpha is equal to L, right? So tan alpha L is equal to L into T minus. We know already tan alpha means T minus capital D by 2L. T minus capital D by, where D is a large diameter element, small d is the smaller diameter, L is equal to the length of taper, capital L is equal to the length of the workpiece. If the taper is turned through entire length, then I is equal to L, small l is equal to capital L. So the amount of set over is given by the equation S is equal to D minus D by 2, right? Again, we can observe this is the workpiece axis and the spindle axis and the tailstock axis. So between these, we are taking a right angle triangle. From this, sin alpha equal to BC by AB. So, but for small angle, sin alpha equal to tan alpha, right? So BC is equal to amount of set over, AB is equal to overall length of the workpiece. The set over S is equal to BC is equal to AB tan alpha. We know AB means capital L. Tan alpha equal to, we know already D minus D by 2. For small angles, L, for small lengths, L is equal to L. So L will be cancelled. So S is equal to D minus D by 2. That is the tailstock set over. This is for the taper is turned through the entire length. S is equal to D minus D by 2. A small example, how can we calculate the S value? A shaft 800 mm long, that means its total length is to be turned taper for a length of 300 mm, that is the small end. The amount of taper is 1:90. Find the tailstock set over required. Tailstock set over S is equal to L into capital D minus small d by 2. So capital L, we know already 800, and D minus D. So that ratio is given 1 by 90, and this is the 2. So this D minus D by L is directly given 1 is to 90. So 1 by 90 is there, so that is 2. So 4.45 mm is the our sector distance between the tailstock and the distance between the tailstock axis and distance between the spindle axis, right? So yesterday we are observing some video. Today we are observing some animation of the 4 methods of taper turning. Taper turning methods. The first one is the form tool method. Here you can observe this form tool. Here it is having inclination angle, inclination shape. So this shape is produced on the workpiece. This shape is up to here only. Up to this width only is produces paper length. Paper length should be less than the tool cutting edge. Right now, tailstock sector method. So this is the tailstock and this is the headstock. So here this is the tailstock, like headstock axis, spindle axis, this is the tailstock axis. This is the workpiece, the cutting tool, it's a check. So this is tailstock sector axis. This is the axis of rotation. Axis of rotation of the workpiece. The taper turning tool, the tailstock. Taper turning operation is done. So it is rotated in anti-clockwise direction. It is rotated in anti-clockwise direction. The workpiece is rotated in anti-clockwise direction. So we are removing the material. So that taper shape is formed. And that taper shape is formed. So axis of rotation of the workpiece are shifted half an angle of taper to the axis. Tailstock sector method, you know already the formula. And next, the third one is compound rest method. We are in this method, we are having some decrease on compound rest, graduated decrease. So, by calculating some angle based on our taper, we are fixing our tool in that angular position. With that angular movement only, we are moving this compound rest movement. Observe here. So here we are removing the nut and rotating with degrees. Which of the taper we need. With that angle we are rotated. So here we are producing taper shape by movement of this compound. By movement of this compound rest, we are removing the materials in the form of chips. Taper attachment method. So this is the attachment which is attached to the cross line. Right? For longer jobs, for lengthy jobs, we are doing taper. Here, the bracket is there. This is the guide bar. Taper attachment is there. On this guide bar, we are having decreased guide bar. You can swing at any required angle of the taper. The guide bar is squirreled. So with that angle is moving. With that movement, we are getting the taper shape. The tool moves parallel to the guide bar to produce these. Right? So these are the 4 methods we have learned yesterday. Now we are moving to another process, that is thread cutting. Before going to discussing about the thread cutting operation, you can observe some pictures of cutting operation. Right? Products of thread cutting. So these are the threads which are formed on the screws, right? Thread cutting. What is meaning by thread cutting? So thread cutting is the process of producing a helical groove on a cylindrical component, right? Thread cutting is the process of producing a helical groove on a cylindrical component. Already this process is observed in our lathe machine operations. To do this process, we have to engage our lathe machine to off nut mechanism. We have to engage the carriage to off nut mechanism or split nut mechanism. Then only we can do this thread cutting operation. The thread pins, those are the helical grooves produced on a cylindrical component. So in this, the saddle receives motion from lead screw. The saddle receives the motion from lead screw, not by our hand. This is the saddle receives the motion from the lead screw by engaging the split nut mechanism. So for that motion, in one revolution of the spindle, the tool traverses a distance equal to the pitch of the thread to be cut. In one revolution of the spindle, the tool traverses a distance equal to the pitch of the thread to be cut. Right? So to do this thread cutting operation, there is a slow motion. There is a slow motion of spindle. Slow speed is needed. Right? So by revolution of one rotation of the spindle, the tool traverses the distance equal to the pitch of the thread to be cut. This is achieved by a gear thread. Okay. So the thread cutting is the process of producing helical grooves on a cylindrical part. So the saddle receives the motion from the lead screw. In one revolution of the spindle, the tool traverses a distance equal to the pitch of the thread to be cut. And this revolution of the spindle, this traverses distance is achieved by a gear thread. So this can be calculated by some mathematical formula. Here the gear ratio is the important for moving the one revolution of the spindle very slow. So that is gear ratio is equal to pitch to be cut divided by pitch of lead screw. Pitch to be cut is divided by pitch of lead screw. That is equal to driving gear teeth divided by driven gear teeth. Gear ratio is nothing but pitch to be cut, that is divided by what is the pitch of the lead screw and how much gear teeth having driving by how much gear teeth having the driven gear teeth. So for multi-starter threads, gear ratio is equal to number of starts into pitch to be cut divided by pitch of lead screw. Gear ratio is equal to number of starts into pitch to be cut divided by pitch of lead screw. That is equal to driving gear teeth divided by driven gear teeth. So here the only word one line is attached in this formula, that is number of starts, because it is having a multi-start threads. Because we are going to produce a multi-start threads, for that reason, what is the gear ratio we have to calculate? Number of threads into pitch to be cut by pitch of lead screw, that is equal to driving gear teeth by driven gear teeth. Why we are going to calculate this gear ratio? After calculating this gear ratio, right? So we are getting the one revolution of the spindle. So with that one revolution of the spindle, the tool traverses a distance equal to the pitch of the thread to be cut. So this entire thing depends upon the gear ratio, right? That gear ratio is to be calculated by pitch to be cut divided by pitch of lead screw, that is equal to driving gauge teeth, it is divided by given gauge teeth. For multi-start threads, number of starts into pitch to be cut divided by pitch of lead screw, that is equal to driving gauge teeth, it is divided by given gauge teeth, right? So you can observe this thread cutting using lead screw method. So this is the lead screw, right? And it is entire thing. It is a carriage, and this is the workpiece which is fixed in the headstock and between the tailstock. So the workpiece is fixed between the two centers. Okay, and this carriage, this entire carriage is engaged with this half nut mechanism that is closed on lead screw threading dial. So this is the half nut operating lever. By rotating this, we are engaging this half nut mechanism, right? So based on gear ratio, based on our gear ratio value, we are adjusting the speeds in the headstock. In the headstock, we are adjusting our gear ratio values uh, by pulling the levers. Here also, we want to engage this half nut mechanism to do thread cutting operation. We have to pull this lever, right? So after engaging this mechanism, so the carriage is moving on this lead screw. So if the carriage is moving on the lead screw, the entire thing is uh, cross slide, compound rest, and the tool post. These entire things are moving on the lead screw only. So the lead screw is rotated based on the gear ratio. Right? Gear ratio is calculated by the formula pitch to be cut divided by pitch of lead screw. So based on that, the spindle is rotated. Based on that, this workpiece is rotated. Based on that, the spindle is rotated. Based on that, workpiece is rotated. Right? By calculating gear ratio, this lead screw is also rotated. Right? So by doing all these things, we are producing threads on the workpieces. We are producing threads on the workpieces, right? So this is the operation, how it can be done. So gear train for screw cutting. So these are the gear trains. This one is the gear. This A1 gear, and this is a B gear. A gear, A1 gear, and B gear. This one is the lead screw, and this is the pitch of the lead screw, and this is the pitch of the workpiece we are going to produce. Pitch to be cut. This is PC means pitch to be cut, and pitch on the lead screw. So here we are providing by mechanism with the gear ratio. Gear ratio we are providing here. We are adjusting adjusting the mechanism. By adjusting to these, the spindle is rotated. So based on that gear ratio, this carriage is moving on the lead screw. By doing so, this we are getting a helical grooves on the workpiece. We are getting helical grooves on the workpiece. So these helical grooves we are called it as a threads. These helical grooves we are called it as a threads. So we are having different types of threads. That is right hand thread. So that means it is moving from right to left. These threads are moving from right to left. And here left hand threads, these helical grooves, this helical shape is moving from left to right. Left to right it is moving, that's why it is called as a left hand thread, and this is a right hand thread. So these are the types of threads, these are the external threads, because these are formed on the surface of the workpiece, and these are the internal threads. These threads are formed in the internal part of the workpiece, right? These are the male thread. External threads are called male threads, and internal threads are called female threads. So gear train for cutting metric threads on a lathe with English lead screw. Pitch of lead screw is given in inches. An additional gear teeth 120 teeth is incorporated in gear train. Gear ratio pitch to be cut divided by pitch of lead screw. that is PC, and PL into 25.4, because this is in inch, so that's why we can convert it into mm. So PC is divided by PL into 25.4. So by we can multiply, we can divide this equation with by 5 by 5. So here 5 PC and 5 into 25.4 gives the 127 into PL. For multi-start threads, 5 into N into PC, that is divided by 127 into PL. So this is the gear ratio formula. That is equal to number of N is equal to number of starts. So find the change gear to be cut 16. Thread down the lathe with 16 lead screw. Pitch to be cut PC 1 by 16. Pitch of lead screw 1 by 6. Driver teeth by driven teeth 1 by 16 by 1 by 6. 6 by 16. That is called A by 6, A by B. 6 by 16, 5 into, we can multiply both with 5 by 5. So we are getting 30 by 80. So these are the teeth we need to cut this 16 threads on the workpiece. So in thread cutting operation, the tool is fed by lead screw. Cutting metric threads and inlet having 127 teeth. The amount of set over required to turn taper 1 is 15 over a length of 300 mm is. So by this we have concluded the taper turning methods and thread cutting operation. So we are having taper turning methods for palm tool method, tail stock set over method, compound rest method, and taper attachment method. After that, we are discussed about the thread cutting operation, right? So these are all operations are performed on the lathe machine, right? Now we are moving to the work holding devices and tool holding devices. In that, we are first we have to discussing about the work holding devices, right? So for work holding devices means, so to fix our job, we need some devices. We need some devices for not moving while rotating, right? For that reason, uh, we need work holding devices. Understood? To fix our jobs while doing the operation, for not producing the vibrational effect by doing operations, we need work holding devices. For that reason, we need work holding devices. So some of the work holding devices are chucks, collets, and centers, right? Chucks, collets, and centers. These are the work holding devices. In that, some of the work holding devices are chucks, collets, and centers. In this, we are going to discussing about the chucks. So work holding devices used on lathe: chucks, collets, driving plates, carriers, rests, mandrels, base plates. So these are all different types of work holding devices commonly used on the lathe machine. Based on our operation requirement, we are using different types of work holding devices, and based on our workpiece sizes, based on our workpiece shape and size, we are using different types of work holding devices, right? In that, we are going to discussing about today's session is checks. In these checks, different types of checks are there. We know already, we are observing figures also of the checks. That is lathe checks. Lathe checks possess gripping jaws. Checks are having jaws. They are capable of holding and rotating the workpiece. On lathe, they are capable of providing, they are capable of holding and rotating the workpiece on lathe. The jaws are adjusted in and out by turning a screw with a chuck key. How the jaws are adjusted? By turning a screw with a chuck key on the top of the chuck. On the top of the chuck, we are having a the chuck is having the top of the chuck. The chuck is having a keyway. So rotating that keyway by keyway with key, the jaws are moving, right? Check key is attached to the lathe spindle, we know already very well. Check key is attached to the lathe spindle with the help of a back plate. Okay, so right, lathe checks processing, lathe checks are having jaws. These jaws are rotated or turned in and out by rotating a key on its top, and these are holding the cylindrical workpieces. Check key is attached to lathe spindle with the help of back plate. The different types of checks are there. The commonly used checks are 3-jaw universal check, 4-jaw independent check, magnetic check, collet check, drill check. Okay? In 3-jaw universal check, all the 3 jaws are moved simultaneously to clamp the one. Check is having jaws, and that 3-jaw universal check is there, 4-jaw universal check. 4-jaw check is there. So now magnetic check, collet check, drill check. Observe here, this is called as 3-jaw universal check. And observe here, 4-jaw independent check. Why it is called as universal check? Means by rotating only one keyway, these 3 jaws are moving at a time. These 3 jaws are moving at a time in and out, right? By rotating a keyway on the top of the jaw, the 3 jaws are moving in and out at the same time. But in 4-jaw independent check, 4 jaws are moved independently in and out. For rotating one jaw, we need one keyway, and the second jaw we need one keyway, and for third jaw we need one keyway, and for fourth jaw we need one keyway. So that's why it is called as a 4-jaw independent check. So before going to discussing about all these checks, now we are moving to the 3-jaw universal check. All the 3 jaws move simultaneously to clamp the work. The job is automatically centered. This chuck is used for holding cylindrical parts or hexagonal work parts. Okay. This chuck is not suitable for irregular shaped workpieces. So this is the 3-jaw check diagram. So these are the jaws 1, 2, 3. And this jaw is having only here one keyway. By rotating this keyway with key, 3 jaws are moved independently in and out, in and out by rotating this keyway with this single key. With single key, these are moving independently. Okay, so that's why this is called as a 3-jaw universal check. That's why it is called as a 3-jaw universal check. So this 3-jaw universal check is used for only used for holding cylindrical objects and hexagonal parts. It is not suitable for holding the irregular shaped workpieces. Right? So these 3 jaws are moved at a time by rotating this keyway. So these are the 3-jaw checks. Based on our diameters, we are having different types of 3-jaw checks are there. So we are fixing our jaw. We have our workpiece in this hole. So after rotating, these 3 jaws are moved. So that is holding the workpieces tightly. 1, 2, 3. So in this figure, we are observing the 3-jaw check is holding the workpiece. The 3-jaw check is holding the workpiece. These are the jaws and this is the workpiece. This is holding the workpiece. And now we are moving to the 4-jaw independent check. In this, all 4 jaws are moved independently, as we learned. It has superior gripping power than self-centering check, but time is more for by using 4-jaw check because all the 4 jaws are moving independently. So to do this by this 4-jaw, we require more time because we have to move all the keyways. With one keyway, it is not moving in and out all the jaws. For moving one jaw, we need one key, and for moving another jaw, we need another key. So for all these jaws, we need for this all this we need 4 keyways. So used for this 4-jaw check is used for holding square shape, octagonal and irregular components. The setting time is more. The setting time is more. Also, it is known as the independent check. Also, it is known as independent check. So this is 4-jaw check. 1, 2, 3, and 4. Every jaw is having keyways for moving in and out. Every jaw is having keyway for moving in and out. Okay. This 4-jaw check is used for holding square, rectangular work pieces and irregular work pieces. All the jaws are moved independently, right? But compared to 3-jaw check, it is very gripping power is more. The gripping power is more in 4-jaw check when compared to 3-jaw check, right? And the setting time is the drawback of this check is the setting time is more because all the jaws are moved independently. So for that reason, all the jaws are moved independently. So for that reason, the setting time is required more. So this is the 4 checks. 1, 2, 3, 4. So by this 2 jars, I am concluded today's class. Today we are learned so far paper turning methods. In the paper turning methods, we learned tailstock sector method. In that, we are calculated S value by doing some calculations. So S is equal to tan alpha d minus d by 2l if the length is S is equal to L into d minus d by 2l. If the length of the taper is equal to the length of the workpiece, L will be cancelled. So S is equal to d minus d by 2. And also we learned the thread cutting operation. In that thread cutting operation, we have to calculate the gear ratio. By gear ratio, we are getting the movement of the spindle. After providing the gear ratio, we are getting the movement of the spindle. With that movement of the spindle, the workpiece is rotated, and after engaging the off-nut mechanism, the cutting tool is also moving in that way. So on the lead screw, by moving on the lead screw, the cutting tool is cutting threads on the workpiece, right? After that, we are moving to the work holding devices. The work holding devices are used to holding the workpieces tightly. We are having different types of workpieces: chucks, mandrels, lathe centers, lathe dog, right? Different types of workpieces, work holding devices are there. In that, chuck is the commonly used workpieces. Chucks are commonly used workpieces. So these are the work holding devices: chucks, collets, driving plates, carriers, rests, mandrels, base plates. In the chucks are the commonly used work holding devices. In chucks, we are having different types of chucks are there: 3-jaw chuck, 3-jaw universal chuck, 4-jaw independent chuck, and magnetic chuck, mandrel chuck, drill chuck, right? So these are the 5 types of checks we are having. In that, today we have learned that we have learned a 3-jar check and a 4-jar check. In 3-jar check, the jars are moved one by at a time by rotating the keyway, right? In 4-jar check, all the jars are moved independently, right? But the gripping power is more compared to 3-jar check. And the irregular shapes, rectangular shapes, octagonal shapes are fixed in 4-jar check. Only cylindrical shapes and hexagonal shapes are fixed in 3-jar check. In 3-jar check, we are not fixing the irregular shapes, right? So tomorrow's class we are going to discussing about the magnetic check and handle check and drill check and the remaining work holding units. Thank you.